Hello everyone, welcome to GGTL Liechtenstein's first webinar. My name is Jana, and I'd like to thank you all for joining us today. A few words about our laboratory before we begin for the people in the audience who may not be familiar with us. GGTL Laboratories formed in 2011 out of the collaboration of two labs, which were both founded in 1996. GemTech Lab, founded by Frank Notary, located in Geneva, Switzerland, and GemLab Liechtenstein, founded by Dr. Thomas Hainschwang in Balzers, Liechtenstein. Both labs are full-service gem testing laboratories that provide a large range of services to the gem and jewelry market, including special services such as Melee-colored gemstone testing and Melee testing for fancy color diamonds. Both laboratories are deeply involved in the gem research, with the GGTL Liechtenstein laboratory particularly active in the color diamond sector. One of the main research projects of the Liechtenstein laboratory for the past 12 years is and has been the Green Diamond Project. Now about the speaker of today's webinar. Dr. Thomas Hainschwang is director and researcher at GGTL Laboratories Liechtenstein. He's been working on the analysis of diamonds, colored stones, and pearls for the past 25 years and is a respected expert in the field of gemological research with the extensive experience in the complex topic of color diamonds. Besides his expertise as a multidisciplinary gemologist with specialization in diamond research and testing, Dr. Hainschwang has developed and built many analytical instruments for gem and pearl testing in the past years, including the photoluminator Raman photoluminescence spectroscopy system, the GGTL DC3 UV-Vis NIR spectroscopy system, and the DFI Deep UV Laser Fluorescence Microscopy and Spectroscopy system, and the Detect Fluorescence Microscopy and Spectroscopy system. These analytical systems have been sold and installed worldwide and can be found in laboratories and at diamond manufacturers around the globe today. He has also published over 160 articles on various gem-related topics and has presented these topics in more than 110 conferences around the world. He received the prestigious Antonio C. Bonanno Award for Excellence in Gemology in 2015 and the Gemological Excellence Award of the Swiss Gemological Society in 2017. Both awards recognize those who have made a significant contribution to the gemological field. Dr. Hainschwang holds a PhD in physics material science from the University of Nantes, France, that he obtained in May 2014 with his dissertation, Type 1b Diamonds, Correlations between the Physical and Gemological Properties of Diamonds Containing Isolated Nitrogen. So today's webinar will be recorded and can be found soon after on YouTube. The Q&A will be done right after the presentation. And to keep up to date on future webinars that might interest you, please follow us on Instagram and Facebook at GGTL Liechtenstein. And please don't hesitate to contact us with any inquiries via email. So now let's begin our Green Diamond webinar.
All right, good evening, everybody. After this short introduction by Jana, I'm very happy everybody is here. Not all participants are in yet, but I think it's 10 past 6 almost. Let's start the webinar rather sooner than later. Okay, so thank you everybody for joining. I hope it's going to be interesting for everybody. I'll be talking about green diamonds and like all radiation related diamond colors. Today I'll try to make it as broad as possible because I know not everybody in here is like a research scientist. So it will be a broadly covered topic with some parts of research obviously involved, but mostly explaining what's the issues in green diamonds and what's currently going on in this highly highly controversial topic of green diamonds and irradiation-related diamonds. So I'd say let's start with the webinar. So give me a second. Okay. Here we go. Okay, so I hope everybody can hear me. Is the sound okay? So I'm going to be talking about the green to greenish blue to yellow green diamonds and our research that we've been doing on these diamonds in the past 12 years. It's actually a collaboration between GGTL Laboratories and George Bossert, who unfortunately died a couple of years ago, way too early, who started in green diamonds, really all that research. But more on that a little later. So first, a couple of words about colored diamonds in general. Why do diamonds occur in virtually all colors imaginable besides colorless? The colorless is what everybody knows. All those colors are much less familiar to many. What's the reason for it? Well, it's actually a range of defects in the diamond structure. There is plenty of different defects, but only some of them really cause color. So most commonly impurities such as nitrogen, boron, nickel, oxygen. Of those, nitrogen and boron are the best known ones to produce yellow in the case of nitrogen and boron in the case of blue. Then we have intrinsic defects. That's like if you don't have a foreign element present, but only a defect of the lattice. So such as vacancies in various configurations. A vacancy is a carbon atom missing in the lattice or having been displaced in the diamond lattice. That's what we call a vacancy. And these are color causing intrinsic defects. And then last but not least, combinations of those impurities and vacancies. Those also cause color. So here, a nice little image to show you what colors diamond occurs in. It's a whole range, as you can see. It's pretty much any color you can imagine, from red through violet, through green, through orange, through blue, yellow, colorless, whatever you can imagine, whatever you can dream of, you can find in fancy color diamonds. Some of them rare, some of them less rare. Now, the color in diamond, it's easy to say, yeah, there is defects, but what do those defects actually do? Those defects in diamond, they give rise to two phenomena, which are responsible for the observed color. These are absorption and luminescence. And absorption obviously in the visible range and luminescence as well. Now in diamond has that rather unique property that luminescence can very significantly influence the observed color of a stone. That's a phenomenon that in the colored gemstone domain, we only know that to some degree from ruby, red spinel, and uranium containing opal. Ruby and red spinel, the chromium gives them a more red appearance through the luminescence, and the uranium containing opal fluoresces strongly green and looks more green than it actually would look without the fluorescence. So in diamond, this phenomenon is very, very common. Let's give an example for one specific defect that causes both absorption and luminescence. So this is the H3 center. The H3 center is it consists of two nitrogen atoms and a vacant position in the diamond lattice, so the vacancy. This little defect is responsible that this diamond has a more or less yellow body color, as seen on the left. But on the left already you can see that this yellow body color is overlaid by green. Now this green color comes from its fluorescence, because the same defect causes very strong green fluorescence. So these diamonds, they are yellow body color from H3 absorption and green fluorescence from the H3 fluorescence. And the combination of it, we'll talk a little later about. Now, how do we measure those defects in diamond? We can talk about them. In diamond, we are in the lucky situation that many defects, we can actually measure them. In many other gemstones, many defects are not measurable by spectroscopic methods. So diamond puts us in kind of a lucky situation in that respect. First of all, I'm just going to talk about like two basic methods to measure those defects. Number one is absorption spectroscopy, and I'm talking about absorption spectroscopy from the UV all the way to the mid-infrared. That's measured by instruments in which light is transmitted through diamond, and after the diamond you measure how much of the light is absorbed and how much is transmitted. Those systems are called UV visible near infrared or infrared spectrometers. Such systems produce spectra, which are graphic representations that show the absorption strength at a given wavelength. So absorption spectra can cover the domain all the way from the UV to the mid-infrared. So we talk 220 nanometers to all the way to 25,000 nanometers. And for diamonds specifically, they're preferably measured at minus 196 degrees Celsius, which is the temperature of liquid nitrogen, and that can be done from the UV all the way to the near infrared. And nobody has to be scared. Diamond resists liquid nitrogen very handily, so there is no problem, never ever damage to diamond just because of that low temperature. Now here, what such an absorption spectrum looks like. Now this is a UV visible spectrum that goes to some degrees into the near infrared. So this is the UV. Here starts the visible at 400 nanometers, all the way to 700 nanometers, and then from 750 onwards is the near infrared. And this spectrum shows you how strongly the diamond absorbs or transmits light. So you can see particularly between 400 and 500 nanometers, the stone very strongly absorbs light, and the rest of the light is pretty much transmitted, which is the reason for the yellow body color of the diamond. Fluorescence is measured by a range of methods, but the most commonly used one is photoluminescence spectroscopy. That's done by instruments that transform the observed visual fluorescence into a spectrum. Again, a graphic representation that basically shows the intensity of the emission at a given wavelength. These are photoluminescence spectrometers. Mostly lasers are used to excite the fluorescence, and diamonds are usually measured at minus 196 degrees Celsius as well. Here you can see on the right side, you can see a diamond immersed in liquid nitrogen and the laser hitting it. So you can see it has a very bright green fluorescence. Depending on what lasers you use, those excitation sources cause much stronger fluorescence than like the typically known UV source used for fluorescence imaging. And yeah, so this is photoluminescence spectroscopy. And this specific stone that you see here in the liquid nitrogen will be represented as such a spectrum as you see here. You see the stone fluorescing, that's a diamond again. And this is the same defect, that's the H3 center, but in fluorescence. So you see the H3 center from 500 to about 600 nanometers, that broad band, that all is part of the H3 center. And on the left, you see the N3 center, which causes blue fluorescence. But since the H3 is so dominant, the diamond basically fluoresces only in green. Now let's talk about this unique group of diamonds with irradiation-related colors. Of all the colored diamonds, diamonds that owe their color to high energy radiation are by far the most complicated ones to determine their origin of color. Actually, all other diamonds, to be quite frank with you, are peanuts compared to these. They're like really, if you have some experience, it's not very difficult to determine the origin of color of the vast majority of colored diamonds, except those. As soon as you have to deal with irradiation-related colors, the story becomes really complicated. The reason for this special status of these diamonds is the fact that defects in color caused by natural radiation are really nearly 100% identical to the defects in color caused by artificial irradiation. Also, a not really helpful issue is that the color of diamonds with irradiation-related color changes when exposed to heat. And that's a valid point for natural irradiation and artificial irradiation. Now, what does radiation do to diamond? If you have a high enough, an intense enough radiation, high enough energy radiation, let's say like at least gamma irradiation or electrons or neutrons, these types of radiation are able to knock out carbon atoms out of the diamond lattice. So knocking out carbon atoms out of the diamond lattice causes vacancies, and these carbon atoms put themselves in an interstitial site, so in a site in between the atoms, and we call them interstitials. The single neutral vacancy, that's how we call it, causes the GR1 absorption. And with that GR1 absorption, you will see mainly a greenish blue color. Now, why are many of those stones green and not blue? Well, the fact that there's two reasons for that. Some samples have significant N2 and N3 center absorption and therefore are green because yellow plus blue equals green. And in others, you will have underlying continuum in the spectrum from vacancy, kind of vacancy clusters. So you have accumulations of vacancies that cause this, they call it like a brown continuum in the diamond spectrum. So that's the reason why you will see green color in many and not blue. So that's what radiation does to diamond. It's a relatively simple defect. It just knocks out the carbon atoms out of the lattice. Now, what does radiation and annealing do to a diamond? If you have diamonds with enough vacancies, like single vacancies, not clusters, and such a diamond is exposed to heat, say about 500, 600, 700 degrees Celsius, the carbon, the vacancies in the lattice start to diffuse in the lattice and aggregate with nitrogen in the lattice when there is nitrogen present. So this kind of a defect, like the H3 center, the H4 center, or the NV centers, cause color and luminescence. I mean, type 1a diamonds, the most important one visually is the H3 center. It's the cause of that yellow body color and really strong green fluorescence. Now here, a little table that shows you that unique group of diamonds with irradiation-related colors. You can see that we have from the left to the right, green, greenish blue, yellow green, and what we call green emitter. Now, obviously between green and greenish blue, there is bluish green, blue green, all that, and different intensities, different depths of colors. But there's basically those groups. You have the green diamonds, you have the greenish blue diamonds, yellow green, and green emitter. And the first three, the green, greenish blue, and yellow green, all have the same color origin. They're all just irradiation. In the yellow greens, quite frequently there is some annealing involved as well, but not necessarily. So they have the same underlying color mechanisms pretty much. In the green emitters on the right side, there is really a combination between irradiation and natural annealing, which is responsible for the very strong green fluorescence of such stones. Now, I show these tables here, so people realize there is stones that people call green or blue, or greenish blue, or green emitter that shouldn't be confused with the problematic ones. So they're neither related and should not be confused with them. A lot of stones out there that people call green are actually more of a olive color or of a yellow-green color. There is a range of color origins for these colors. So first of all, the greenest of the non-irradiation related greens that I've seen are the yellow-green, yellowish green stones with a nickel-related color origin. Relatively rare, relatively unusual, but they occur. They're not at all to be confused with the greenish blue diamonds, because those irradiation-related blues are never straight blue, but they're always kind of greenish. Not to be confused with those are the regular blue diamonds, the boron-related blue diamonds. That's a completely different type, no correlation whatsoever. The irradiation-related blues have no boron whatsoever, so not to be confused. Then very common thing, especially in melee sizes. In melee sizes, you often receive things that people say, hey, we have green diamonds, and then you receive stones, and you're like, yeah, they're olive, they're not green. So what we call olive is really a mixed color between yellow, brown, and green. And when you look at them very closely, you'll see that most of them are more of a yellow brown or yellow gray with some green in it. The green is really minor. So these olives are either nickel related colors, plus hydrogen might have a certain role in those colors, but nickel for sure. There's same subtype of the nickel related on the left. And you also can have single nitrogen plus deformation resulting in olive color. So that's two types that you commonly see. And then on the far right, you have a green emitter, visually quite similar to what we saw on the other table. But these green emitters, their body color is not as clean. They're very commonly, these green emitters are kind of brownish. And their green fluorescence comes only from plastic deformation. So it's basically a brown diamond that has been submitted to very strong plastic deformation and possibly distinct annealing, because the H3 sensors in those stones are very strong. As you can see in the image underneath, you can see that the brown graining with weak light, the brown graining is brown. As soon as you shine in a strong light source, it fluoresces green, and you can see the green lines of the graining. So now the question is, why is that determination of color origin of such diamonds so important? Well, I mean, naturally colored diamonds of the green to greenish blue to yellow-green group are super rare and highly valued. Some more, some less. The most famous one, 503 carat fancy vivid green diamond, the AURORA green, went for $16.8 million. If you calculate that on a kilo of vivid green natural diamond of natural color would currently cost around $16.7 billion US. So it's quite a value. Now, the thing is, if such a color, if you have a 5 carat diamond of equal color or very similar color, treated with a treated color origin, the value of the stone is very significantly lower. So you'd basically get it for around $30,000. You count maybe a MNOP color diamond or a brownish 5 carat diamond, irradiation cost, and that's the cost of your stone. And that's why it's so important that we can accurately identify such stones as naturally colored without any ambiguous results. Now, why is the determination of color origin of such diamonds such a problem? As I kind of mentioned before, it's really easy to treat diamonds with irradiation and annealing, so they turn green, greenish blue, or yellow-green. You just need access to an irradiation source and or maybe also an oven if you want to anneal afterwards. And there we go. You can make your green diamond out of pretty much any color you want, as long as the original body color is not too strong. The defects caused by artificial and natural irradiation are virtually identical. Mentioned that before. Annealing of irradiated diamonds creates virtually the same defects, no matter if this occurs naturally or in a lab furnace. And that's what causes the problems. Now, what results out of this extreme similarity between natural colored and treated diamonds? Well, we have many, many diamonds with the color origin undeterminable. There is plenty of dubious diamonds with reports indicating natural color origin. There is plenty of natural colored diamonds with reports indicating undeterminable color origin. There is plenty of natural colored diamonds with reports indicating treated color origin. And there is actually also quite a lot of naturally colored diamonds that during the manufacturing process are identified as being natural. And then as soon as they're finished, they're being identified as either undeterminable or even treated. So you see, the problem is quite a serious one. I'll show you an example from 2014 that we had actually here at the lab ourselves. We received 2 diamonds without any mention of the client about the stone itself. Just that one stone got a report from a lab X as natural, and one report got a report from the same lab X undeterminable. Well, we tested the 2 stones by absolutely every method possible at the laboratory. I just show you 2 overlays here of an infrared spectrum and a UV visible spectrum of the 2 stones. The 2 stones were also the PL spectra are not shown, but on all the spectroscopy that was done, you could absolutely 100% overlay the spectra on top of each other. They were identical. Fluorescence imaging was done. The stones were obviously from the same rough. So how can this happen? Now, this is a kind of troubling case. Why can this happen? Let's talk a little bit before I go into what we did to tackle this topic. Let's talk about what treatments exist to create green to greenish blue or yellow-green color in a diamond. Let's start with the earliest one. The earliest treatment out there is from about 1900, from the early 1900s onwards, are diamonds irradiated in radioactive salts, mostly radium salts, but there were also other salts were also used, but radium salt is the most typical thing that was used. So those stones were directly immersed in the salt, so they had direct contact in the radioactive salt. The causes them to be irradiated very strongly by alpha particles. Alpha particles do not penetrate inside the diamond very deeply, but only very, very shallow. So this treatment causes the carbon atoms to be displaced only in the surface or very close to the surface, gives you a green to greenish blue body color, surface coloration, or very close to the surface coloration, a very shallow layer. This was the only treatment available until about 1930. And it has the unfortunate side effect that all stones treated by this method turned radioactive. And they turned radioactive for a very long time because the half-life of radium is very long. So after thousands and thousands of years, such stones will still be radioactive. Some of them are only very weakly radioactive, particularly the clean ones. Clean stones have very low radioactivity generally. As soon as you have stones that have fissures in which radium salts were trapped, you get really high activity in such stones. So here we have a pretty extreme example, a half character with an activity of 20,000 becquerel, which is pretty extreme. That's about what you find in the old watch in the old watches, you know, the fluorescing numbers. When you take the watch glass off and you take a Geiger counter, that's about the activity you have in there, because they also used radioactive substances directly to make those fluorescent numbers. So such stones, I must notice here, not that somebody will be scared, this is very, very unusual to see those today in the market. Nobody does that anymore. It's very, very uncommon. From about 1940 on, cyclotron irradiation by alpha particles, deuterons, and protons was used to treat diamonds to create also a relatively shallow layer of color. Those elements, those particles also do not penetrate deeply inside the diamond, cause just a surface layer. You can see here on the right side on the image, you can see the typical umbrella effect. So around the culet, you see this color concentration. That is very typical, very characteristic for such stones, and identifies them straight away as treated. Again, I said just shallow surface color. On the left, a 60-inch cyclotron, like one of the earliest models and one of the most powerful at the time. That's the kind of instruments that were used to irradiate diamonds this way. In contrast to radium-treated stones, such diamonds did develop some radioactivity, but only very short-lasting. So that was not really such an issue anymore. Now, by 1950, the cyclotrons were pretty much replaced by electron and neutron irradiation. Electron irradiation, on the left side, you see two electron accelerators. The top left is a 10 MeV cyclotron, and on the right side, a variable energy accelerator that runs from 1.5 to 2.5 MeV, I believe. These are the accelerators that we use at the facility in Switzerland to get diamonds irradiated by electrons, at least. Those are two modern ones. And on the right side, we see a nuclear reactor with the typical Cherenkov radiation. From the standpoint of safety, the electrons are the safest source of irradiation. Diamonds are not turned radioactive unless you start using sources of way above 10 MeV energy. Everything below is absolutely safe, and diamonds are not radioactive after the treatment. In neutron sources, diamonds, especially included diamonds, tend to be radioactive, but only for a short period of time generally. If you use clean diamonds, they're typically not radioactive for any significant period of time. So today's market, the vast majority of irradiated diamonds out there are electron irradiated because it's a very convenient method. You can just turn the source on, turn it off, go in, look at your stones. If they're good, take them out. If they're not yet, you can go out, turn the source on again, and so on. So it's really easy, and can't do that in a neutron source. Wouldn't want to walk into a reactor. Okay, now another way to create greens is irradiation and annealing, all the way up to 1600 degrees. This is basically done in a laboratory furnace. Obviously, from about 500 degrees onwards, you need to protect your sample better even before, so it doesn't burn or evaporate. The sample on the right side is a typical product of an irradiation plus annealing at about 800 degrees. You're creating the kind of green fluorescing green emitter diamond by this treatment if you're using the right source material. And a more exotic way to create green, it's more of a drab green color that's created by it, is when you heavily irradiate a diamond and then you anneal it at about 1500 degrees Celsius. We call them H2 green diamonds because their green color is just from the H2 center. That strong broad band that you see here in the spectrum that cuts out the entire red portion and orange portion of the spectrum. And just transmits some green in your stone. That's why you call this green, this deep dull green color. From about 1998 on, we have HPHD treatment. Now HPHD treatment just creates green emitter diamonds out of brown type 1 stones. Well, that's the only kind of green you can get out of by HPHD treatment. So there's no other way to get green color. Okay, now question. GR1 related color. GR1 is the color, the defect that causes all those the greens to the greenish blues. That's GR1 responsible for that color. GR1 related color, is there such a thing from another treatment? There's a very simple answer: impossible. GR1 and actually all other defects induced by irradiation are notoriously unstable to heat, and any involvement of excessive heat will destroy the green to greenish blue color. There is no way to introduce GR1 and associated defects in a diamond by a non-irradiation related process. Obviously, you can play with various combinations of irradiations, annealing, HPHD, LPHD treatment, but the underlying fact remains that stones must be irradiated to exhibit sufficiently strong GR1. So you have that kind of a stone, it must be irradiated. Okay, and now let's get to the green diamond and associated diamond treatment project. The goal of this project, as you can see from the introduction, was to create a much more consistent identification of color origin of diamonds with radiation-related colors, and get a much more profound database on the effects of irradiation, annealing, and also HPHD treatment on the effects. So the steps of the study are these three. So one step is the analysis of natural green to greenish blue diamonds and green emitter diamonds from museum collections and collectors and of stones of known natural color origin. Analysis of treated greens to treated greenish blue and green emitter diamonds. And then probably one of the largest treatment projects ever to cover all types and colors treated by irradiation and annealing all the way up to HPHD. That's the project. Now, the history of this green diamond project is quite long. It starts way before I was even in gemology and way before our lab even existed. It started actually 8 years before. George Bossart is the pioneer in this. He was interested in green diamonds and had that dream to analyze the Dresden green by UV visible spectroscopy, which was quite a thing to do in 1988. Furthermore, he had to do it in Dresden. So he had to get into Dresden, which was at the time behind the wall. So as you imagine, that might have been, that was quite a venture. And that has started his deep interest into these diamonds. George worked on this topic more or less as a lone fighter all the way until 2009, until he invited us to collaborate with him on this topic. So the Green Diamond Project, as we know it, was started in 2009. The George Bossart Natural Green Diamond Collection has been part of this project ever since and remains so today. George died, unfortunately, in 2012. So unfortunately, we only collaborated with him for 3 years, but at least we could visit one of the museums together with him. So we visited between 2011 and 2015 various museums to test natural color green to greenish blue and yellow green diamonds. And we did so with George in 2011. Frank, myself, and team members of GGTL were on the road in 2012 and 2015. In 2015, actually pretty much induced by that example that I've shown before of those two diamonds from the same rough that had two different reports, we decided to go deeper in this project and launch a really big treatment project. And this is what we have been doing ever since. So since 2015, we've been deeply involved in diamond treatment and their characterization. Now let's have a look through the steps of the project. First of all, the analysis of natural greens and associated colors. This is going to be quite a lot of images of antique pieces. Here we go. So 2011 and 2012, Natural History Museum, Vienna, historical fancy color diamonds. Now, for everybody who doesn't know, this museum has a pretty spectacular collection of fancy colored diamonds. Thanks to the royal connections between Brazil and Vienna and Austria, they have some amazing pieces. So we went to Vienna on site, both times by car, filled the car with all equipment you could possibly get into the car, and analyzed the diamonds on site. Those diamonds are all mounted, so we had to analyze them in the mounting, which is pretty challenging, especially when you look at the little brooch here on the left, center left side. There is stones that are, the smallest ones are maybe 10 points. And we achieved to do the UV visible, PL, infrared, and all that for these diamonds at low temperature. So these stayed mounted and in Vienna, so we had to do it obviously on site. Here, now I'm gonna run through a couple of slides with beautiful pictures of those amazing pieces. Here, this is prior to 1805. Amazing piece with a beautiful green on the left, an amazing blue in the middle, and on the right side is one of those brown, orange-brown, strong green fluorescing stones. You can't see it here, but with a strong incandescent light, the stone glows green. Here, a brooch with various diamonds, pink, green, colorless, and there's like bluish green, greenish blue. There's like 4 or 5 greens on this piece. Also very old. Here, 3 diamonds with green, 3 rings with green diamonds. All these are, they're either from India or from Brazil. Here you can see the original description. The top one you can see, it says India, diamond green in the ring. And the bottom one is India as well. So most of them date prior to 1805. So pretty amazing pieces. Sorry, I didn't want to do that. Here we go. That's a selection of green emitter diamonds, also very old, same type of period. The bottom one is more brownish, but still with very strong green fluorescence, and the others are yellow body color with strong green fluorescence. Here, 2 pieces of rough, one a little younger from 1907, the other one didn't have a date, but they're natural green emitters. You see again the original description of the stone. Beautiful piece, beautiful historical diamond. And we were allowed to cool them down, which is not something that every museum would let us do. So yeah, this is you got to be quite fortunate that people trust you on that. Many people in museums have that funny idea that liquid nitrogen will damage their precious diamond, but well, examples have shown that even heating a diamond and throwing it afterwards in liquid nitrogen doesn't damage them. So diamond is extremely inert to thermal shock, so you can do pretty much whatever you want with it except burning it. Just a couple of slides to show what we did. We did obviously spectroscopy. So here you have 2 examples. On the top face shows you the UV visible spectrum with a strong GR1 band of this green. And on the bottom, you see the UV visible spectrum of this fluorescent green with a strong H3 center responsible for the color and the fluorescence. Here, one example of a green of the PL that we did on site. So here in this occasion, we did 1, 2, 3, 4 different lasers. This is 405, 473, 532, and 635 nanometer. So we pretty well tried to characterize those diamonds as well as we could on site. 2015, as another example of our museum trips, was the AURORA collection and historical green diamonds at the Natural History Museum in London. Here as well, this was even more brutal than the Vienna trip, because in Vienna, at least you can put your car in Austria on a train and go sleep and wait until you arrive in Vienna. You can't do such thing in London. So that car was filled by equipment again. And then Frank and Candice, they drove and I flew. I said, I'm not going to drive. So they drove by car from Geneva to London, which is it was quite a story. There we go. You see the unpacking. So we got the material out of the car, everything through the halls of the museum, the underground halls. This is Alan Hart, as you can see, Alan Hart and Frank Notter in the left picture, pulling the piece, all the valuable equipment into the halls where we were allowed to test them. So we had to set up all the goods on site, here you see. So we brought everything from fluorescence microscopy and spectroscopy through photoluminescence, UV-vis, infrared, everything. And we were working actually in a team here. Took us a day to install all the equipment, a day to get all the equipment out again. So we were on site for a total of 7 or 8 days. And with the help of Alan Hart and also Sonal Rege Delpech, Sonal Rege, we tested as many diamonds as we could. So we had a total of 300 diamonds that we tested in 6 days. Part of them were the greens of the Natural History Museum, and parts of them were the stones of the AURORA collection of Alan Bronstein. One amazing thing about this London trip was our hotel room. It's the 7 nights in the absolutely smallest hotel room I've ever lived, ever stayed at, for the highest amount of money per square meter. So this is the view out of the restroom / shower. You see the door couldn't be opened because the bed was right there. So this was an interesting trip as well. Let's have a look at the pieces we analyzed. We analyzed 295 natural fancy color diamonds of all known colors except red. There's plenty of greens in there, green emitters, etc. So that was a very interesting collection to work through. For most of the stones, almost all testing has been performed. And then obviously of great interest for us were the natural color green diamonds at the NHM in London. There aren't that many. There were 4 faceted natural color green diamonds, one date prior to 1850, one prior to 1934, 2 prior to 1934, and 1 1957. So those dates are all reasonably safe to be sure that they're absolutely not treated. Again, they were tested by all methods that we had available. Testing procedures at the NHM, I'm not going to go into details. I've told you all spectroscopy. So it's just a lot of spectra, 185 spectra here, 190 spectra here, 335 spectra here, 250 fluorescence images. And we used 35 liters of liquid nitrogen in those 7 days. So it was quite something. Step 2, testing known treated diamonds. That's just like a little step, you know, certain diamonds that you receive, you're absolutely certain that the stones are treated, specifically those ones. This one, we were allowed to test it at the Natural History Museum in London. The Crookes diamond, That's a Crookes diamond that was treated in radium treated in 1916. You can see it's also colored by GR1, like all other greens. And you can see the photoluminescence spectra of the Crookes diamond. Very interesting piece, still radioactive, not very strongly, but it's a little radioactive, a nice little octahedron. Then we have received over the years from time to time particle accelerator treated stones like this one. This is like a really big one. So this is like, I think this one was almost 50 carats. Very shallow coloration near surface. You can see the umbrella effect in all images. On the image top left, you see the color layer, how deep it is. So it's really not deep. And then on the bottom left, you see the nice umbrella effect. On the right side, you can see that hitting with a laser at the edge where you have the color, you got green fluorescence from the defects introduced by the particle irradiation. Another example, again, you see that on the right side, you see the umbrella effect in those stones. An example of a stone that was treated by electrons, by very weak electrons. Usually, I have to say the electrons used are strong enough to penetrate relatively deep inside the diamond. We're talking millimeters, several millimeters quite quickly. So this one must have been treated with really low energy electrons. You can see in the middle image, on the right side, you can see the layer of blue color under the table. This is something that generally you cannot see in irradiated blues. Now, step number 3, the GGTL diamond treatment project. Now, this was some insane idea we had in 2015. And it is still ongoing, but we have very, very much evolved in this project. By now, we have treated a total of 180 colorless yellow, brown, olive, gray, and violet diamonds, all different diamond types, including subtypes. So there's type 1A, type 1B, type 2A, type 2B, everything in between. We've tested them prior to treatment by all methods we have available. And we have installed systems and methods of testing that we haven't even known about before. So we have all this spectroscopy and all this imaging from those stones prior to treatment and then post-treatment. And what did we do? We treated part of the diamonds by the relatively low energy electrons, part of the diamonds by much higher energy electrons. Some diamonds were treated by neutrons. We have diamonds that were at least attempted to be treated by gamma irradiation. Gamma irradiation is a very, very, very low efficiency in creation of vacancies, and in consequence, it's extremely difficult to get green out of a diamond by green or greenish blue out of a diamond by gamma irradiation. And after those treatment steps, each of the stones was heat treated from 140 degrees onwards, some stones even lower, all the way up to 1,600 degrees Celsius in 100-degree steps. And some stones were HPHT treated at 2,000, 2,250, and 2,500 degrees. Certain stones were re-irradiated post-HPHT, and some were re-HPHT'd post-HPHT. So you imagine what we've done here. After each single step, we had to re-record absolutely all the data, which is, in the end, an enormous amount of data. On the bottom, you see the kind of treatment methods we have used. On the left, again, the electron accelerators. In the middle, high temperature furnace. On the right side, an HPHT press in Switzerland. Let me show you an example of what's happening. I'm not going to go much deeper in the treatment project because it's just going way too far. But basically what we did, we irradiated and annealed every single sample and recorded all the data. How does that look like? Here an example. You can see the diamond before was perfectly colorless. It was type 1AA. This one was treated with 10 MeV electrons, I think for 2 hours, if I'm not mistaken. So after 2 MeV electrons, the stone turned greenish blue. As you can see, green blue, greenish blue. 260 degrees, the color changed already relatively significantly, surprisingly, in this stone. 350 more, 450, 550, well, you know, at 450, it's pretty much the same as at 350. And at 550, you start seeing a change in color. So the stone goes way more towards yellow. So 550, 650, that temperature limit is about the limit where the vacancies in the diamond start to migrate and form new defects. And you can see it every time. You can see it down in the spectrum what happens. So before there's not much. After radiation, you have GR1. And then the more you heat, the more GR1 disappears and you form H3 and sometimes H4, which are responsible for the yellow color in the end, if you have a type 1A diamond. And this is the basic thing that we did. So it's not just limited to UV visible spectroscopy, but it includes much, much more than that. So here you have the same sample, the exact same sample in fluorescence. So this stone, after irradiation, developed this greenish blue fluorescence and then went back to faint blue. And at 550 at the dot, you see where you form H3 in this specific sample. And H3 becomes strong from 650 degrees onwards, and that's the temperature threshold when you get your yellow color. And you can see that the defects created that we can detect by photoluminescence spectroscopy, they're quite unstable. They're like at very low temperature, they start to change very dramatically. And as expected at 650, you get that strong H3 peak. Which then dominates the spectrum until very, very high temperature. Here, just to show you the kind of imaging work we did. This is from left to right, you can see long wave excitation, short wave excitation, and before treatment all the way to 650 degrees Celsius. So you can see the stone on the deep UV looks blue under most conditions and then goes green at 650. And under long wave, you have different response. So in all those defects, you can nicely characterize them. We're using fluorescence imaging as shown in this image. Here, just a little overview of what we produced. So this is what happened. We had some stones that were green, some are greenish blue, some are almost blue, as you can see here in these samples. And some of those samples are obviously heated. So the type 1B diamonds, they all turned purple to pink. The type 1As all turned yellow after annealing, etc., etc. So this is a nice overview of what kind of color we created by heating by irradiating and then heating. Okay, now let's get to just a word about data processing. You can imagine that the many thousands of spectra and images of natural and treated diamonds needed and still need to be processed to extract the important data and to understand all the correlations between the defects, the diamond color, the diamond type, and treatment conditions. And finally compare them to the data of known naturally colored diamonds. This is what we have done. And during this study, it's extremely challenging to draw an accurate conclusion out of what can be observed in the huge amount of data that has become available in this 12-year study. Just to give you an idea, one single treated sample has currently 250 spectral and imaging files associated with it that need to be processed and correlated. Without going into details, it can nevertheless be stated that the Green Diamond project has produced a huge database with a series of new criteria that allow us to work seriously on the color origin determination of such diamonds. And that's what we always wanted to do. Okay, now our conclusions. Yeah, I've shown in this presentation that green diamonds and all other colors related to irradiation, natural and artificial irradiations, are really problematic. It's not an easy topic. Not many dare to tackle it. Not many do. We decided to put a very significant effort into this topic in these past years, and we have accumulated an extremely large amount of valuable data about those natural color diamonds, plus the creation and behavior of the effects of diamonds upon irradiation and annealing, all the way to HPHD. The data is of utmost importance, because if I show just few spectra in this presentation, not to overwhelm you with spectra and things, I can tell you that comparing spectra of natural and treated diamonds is like comparing an apple from the tree on the left with an apple on the tree on the right. They're 99.99% identical, and you are there to find the little difference. You're there to determine what little difference can possibly tell you if the stone has been naturally or artificially irradiated. So besides the commercial importance, this study has uncovered and is uncovering interesting and unusual features, such as uncommon behavior and defects and unusual reactions of diamonds. At current stage of this ongoing project, GGTL Laboratories is able to consistently identify the color origin of the vast majority of radiation-related greens and greenish blue diamonds, and also green emitted diamonds. And I believe this finishes my presentation. I would think we go into the Q&A from here on. So please put questions into the Q&A section and not into the chat. I'm gonna check the Q&A. Okay, there we are. How much? Okay, I'll read out the questions and I'll try to reply all of them. We have about half an hour for 25 minutes for questions. Okay, the one question was what's the cause of color for chameleon diamonds? Yeah, actually I forgot to put those in the greens that are not to be confused with the radiation-related greens. Sorry for that. Should have thought about that. I worked on those for a while. So the cause of color of chameleon diamonds is currently still pretty much unknown. Those diamonds are pretty rich in nickel and pretty rich in oxygen. The oxygen content, there is a lot of debate if it causes color or not, but it just can be stated that it's the combination of oxygen plus nickel in the chameleon diamonds must have something to do with the color origin, with the cause of color of those diamonds. There is no other clue so far that would tell us something else. Those diamonds are mixed between hydrogen rich, but actually they're more nickel rich than hydrogen rich, and 480 nanometer band diamonds. How much radiation can harm diamonds? Can harm humans? Oh, can harm humans? Well, it depends how long let's say it this way. If you have a radioactive diamond, even one that has a radioactivity of 20,000 becquerel, these stones are very small. If you take such a small diamond, you put it on your desk, you take a Geiger counter, you go straight to the diamond, let's say half an inch from the diamond, you're going to have 20,000 counts. If you go with a Geiger counter, maybe 20 centimeters away from the stone, you're going to have 100 counts. If you're a meter away from the diamond, you're going to have practically zero. So those diamonds by themselves are not dangerous to humans. If you wear such a diamond in a necklace straight on your neck for 20 years in a row, I would think it would probably have some effects on you. So I just wouldn't do it. Absolutely not. Radiation is always something, it affects one human more than others. So, you know, it's something that you just shouldn't kid about and shouldn't play with. Okay, next question. How is the assignment of a particular zero phonon line done to a specific defect? Is this through ab initio calculations? Yeah, that's modeling. That's the hardcore physics, the hardcore theoretical physics people that know how to do that. I don't. So the assignment of particular CPLs, first of all, you can speculate on it based on analytical observations, which is basically what we do. You analyze stones by all means possible and conclude if there is any other elements present that could cause certain defects, certain peaks, and certain ZPLs. You just see them and you see there is no nitrogen in a stone. So you pretty much safely can safely assume that there is no nitrogen involved in the defect. So yeah, it's to a certain degree, you have to make reasonable assumptions through analytical work, and then people make calculations to see if those assumptions might work. It's like the 480 nanometer band in diamonds. Is it oxygen or not? We made not us, but a group we worked with made calculations that it actually could work. Other physicists have made calculations that related it directly to oxygen. And then you test the stones, you test them by chemistry, you find elevated oxygen at concentrations in such stones, and then, well, you can relatively safely assume that you have oxygen-related defect. To finally get the real structure of such a diamond is even going beyond that. There's very, very few defects in diamonds where the actual structure is known. You can read through all those books that show the different defects, and the structure remains a speculation for many of them because it's not such an easy thing. And then the next one is the Brown continuum proven to be vacancy cluster related beyond doubt through extensive TEM analysis? I don't think so. Charged nitrogen C defect is related to this absorption? No, I don't think so. There is a single charged nitrogen C defect. No, you would detect it. The C defect, you would detect it even if it was present in very low concentrations. So this is extremely unlikely. Does the irradiation for color change only apply to natural diamonds or only to those made in the laboratory? Well, actually, it does the same to both. So if you have if you take a synthetic diamond and you irradiate it, it turns green or greenish blue, depending on what irradiation you use. If the stone has some single nitrogen in it, you heat it, it turns purple or pink. So they do the same thing, you know, depends what defects you have present, on how they react on annealing, but they basically do the same thing, natural and treated. Okay, do you know about GI's recall of some green diamonds? Can you comment on that? Yes, I know about it. Can I comment on that? And no, I can't. I don't know. I really don't know what happened. GI can comment on that themselves. Sorry. Okay, Mike Green. So how do you tell the difference between a naturally irradiated diamond and a laboratory irradiated diamond? You talked a lot about collecting atomic data, but not about how you actually make the separation. Yeah, I know you would like to know that. Sorry, but that's not going to go out anywhere. Are those data available to the public, spectra, etc.? Not the data that we have taken from natural diamonds, and only limited amounts of the treated ones. Nutrient dollar. I understand green needs irradiation defects. So what type of natural radiation causes natural green body color? Yeah, well, by far most greens have a surface color from alpha particles. That's, you know, those green coated diamonds that we see particularly in Brazil so frequently. In order to get green body color, you need very likely the radiation responsible for is gamma irradiation. Gamma irradiation penetrates through, goes through a diamond like, basically like light. But it has a very, very low cross section, so it has a very low efficiency in diamond to create defects, which means gamma irradiation needs a very, 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 very long time to create green diamond, green color in diamond. So in natural diamonds, this is likely the main cause of the green body color. In artificially treated stones, I have not achieved to produce an actually green color using gamma irradiation, even after more than a year in a gamma source. Does radioactive material can't be a single test to identify treated greens? No, they're not radioactive. So it's like most treated diamonds are not radioactive. If you have a radioactive diamond, you know it's treated. So as soon as you can measure the radioactivity, you know the stone is treated. If it's not radioactive, you don't know. How much time does it take to carry out an identification analysis? Oh, that depends a lot. Sometimes when you're lucky, you get a stone which has been particle irradiated in a cyclotron, and it takes you 5 minutes to identify whether a stone is natural or treated. You just look at it under a microscope. And then you get those stones where that stay in your lab for weeks and weeks and weeks, and you still don't know what to do about it, because it just takes all your time, all your thinking. You try to figure out what to do about it. So it might take very long, it might take very short. Will we ever be capable to identify natural versus treated in these specific colors? For some, yeah, but not for all. Is it true that the umbrella effect pattern varies depending on whether a stone is rated face up or cured up? Yeah, absolutely. Yeah, so it looks very different depending if the stone was upside or down, if the cured was up or the cured was down. If the cured was up, then you have the umbrella effect. If the cured was down, then you just have to look the other way around, and you're going to see it on the table side. In 5 MeV treatment, is there any safety records you can share? Never seen any problems. I mean, we have treated plenty of diamonds at 10 MeV and never had the slightest residual radioactivity in it. So we, generally speaking, you have to be worried about radioactivity in electron treated stones if you exceed 10 MeV. So if you go above 10 MeV, then you know you got to check. But below that, no problem. Half width, full width, half maximum as a relevant indication for this type of irradiation. If I consider full width, half maximum a relevant indication for this type of irradiation, no, not at all. The full width, half maximum depends on all kinds of factors. So depending on how many defects you have present, how strong is the irradiation, what type of irradiation do you have, how much nitrogen do you have, impossible. It goes from X to Z. So you have all types of full width half maxima in these stones. What do you believe could have caused the latest recalling by GIA of natural color origin certificates of green diamonds? I really can't reply to that question, unfortunately. I would like to know it too. I guess they will clarify that, hopefully. If you irradiate a type 2A diamond, it will become green or just blue? Oh, it depends how you irradiate it. If you heavily neutron irradiate a type 2A diamond, it will go green. If you just electron treat it, it will likely be blue, greenish blue. So it depends on the irradiation. You know, if you want blue, you use typically lower energy electrons, and if you use very high energy electrons and heavier irradiation, you cause more chaos in the stone, you cause more vacancy clusters in the stone, and you'll create more of a green color. So that really depends on what kind of irradiation you use. In your opinion, in the near future, will problems of green diamonds origin end? It will be possible to identify 100% the natural and treated diamond. As I said, in many cases, I think it will be. It's possible. In some cases, absolutely impossible. So there is just stones where there is just no difference whatsoever. So in some cases, you just can't. What comment will you state in the GGTL report if you do not reach the cause of color green, colored diamond, and is this acceptable in gemological laboratories worldwide? Well, we use undeterminable just like all others. So that's the acceptable term to use. Unfortunately, this is still what happens for certain stones. Brown continuing CVD diamonds. Okay, well, in CVD diamonds, I'm not 100% sure about that. But that's not the same type of continuum as the one that you see in the green diamonds. I understand that you do not want to share the secrets how to differ the natural from the irradiation, and it is possible to see the difference. Yeah, for some stones, it's absolutely possible. For some stones, no. For some stones, we still haven't found any significant difference. For some stones, absolutely yes. The greens from Zimbabwe are different from the South American greens. Why is this? Good question. Different origin, different conditions, different conditions. You know, under what conditions were they irradiated? For how long were they on the ground? How much heat did they get? That's why they differ. And yeah, that's the difference between them, and we see differences indeed. It is correct to say that most safe laboratories to state whether green color is natural or artificial are GGTL and GIA. I don't know. I don't know. That's up to the client to decide. Is there operator mine that source natural green diamonds today? I'm not sure what that's supposed to mean, but there's several origins for green diamonds today. So there's Zimbabwe, there's Brazil. There's others. That's not all. There's other mines that produce green diamonds. Do you plan to publish an article about your great work? Yeah, it's absolutely in plan. No promises when, but it's absolutely planned. How frequent do you think that laboratories did mistake detect the color origin of green diamonds? I think it happens quite commonly. I do not think it happens too commonly. It's not very common that naturally colored diamond, actually treated colored diamonds get a natural call. I don't think that that's very common, but on the undetermined versus natural calls, I think there is quite a lot of errors that happen, but it's just because it's really difficult. Okay, how often in the last 10 years your GGTL lab had to issue undetermined and color origin of green diamonds? Oh, good question. I don't know. I mean, you know, we're not perfect either. I mean, we had stones where we were convinced they were treated and we had to change our opinion because we made progress in our research. We're not perfect. We also just work hard to find a solution for the market, because that's all this is about. We want to find the solution for the market on a problem that's beyond anything that most people can imagine. I mean, I can just tell you, determining the origin of color of a pink is, I don't know, it's so much more easy. The greens are way and beyond of anything you can imagine in complexity and difficulty for the identification of origin of color. And I think that was the last question on here. Yeah, last question. All right. Okay. All right. So I thank you everybody for listening for this hour, now almost hour and a half, to this webinar. I hope you learned something from it. I'm sorry that I didn't give away all the secrets that we found in 12 years of work, but that would be kind of easy if you have to work 12 years to find out how things work, and then you just give it away so everybody else can use it. So I apologize on this side for not having been open about what exactly we found. Well, I hope to see some of you or all of you in shows and then on the road again as soon as we all can travel again. And I thank you very much. And bye-bye.